I guess like after I start my presentation, I will start my work so I can know. Like,
okay, that's good. Yeah, typically people come a couple of minutes late.
Yeah, totally understand that. Do you think that this position works fine for this microphone?
I think if you think that your voice is a little bit lower, then a little bit more. Yeah. Yeah. So your name is Yifan, right?
Yeah, Yifan. Yeah.
I can pronounce. My name is much higher.
Like in Chinese, Yifan, like Fan is like difficult for others to pronounce. So for when I say like my name is Yifan, Fan is like US people can pronounce that.
Yeah, I think that is See, now people show up.
Yeah.
So that's why I always have to. Yeah, you may turn on that one. Okay, so thanks for joining Computer Science Colloquium. So today's speaker is Yifan Gong from Boulder Research. She received her PhD in the electrical computer engineering from Northeastern last year. And her research focused on advancing AI system for efficient deep learning on edge devices, bridging the gap between algorithms and hardware. So she just selected as the 2024 ECS Rising Star and also ML and Systems Rising Star. Welcome, Eva.
Hello, everyone. It's my great pleasure to be here to share my work, Advancing Efficient and Trustworthy Deep Learning for Sustainable AI Systems. So nowadays, we see actually deep learning is everywhere. It has broad application scenarios, and we see there are many different application scenarios, such as autonomous driving, healthcare, speech recognition, and it can also be used for some applications relevant to our ecosystems. We can use it to help weather forecast, and we can also use it for climate change predictions. So behind this evolvement of deep learning, nowadays we observe there are two trends in the deep learning area. The first trend is the ever-increasing model size, especially for these nowadays generative AI models. So if we take text model as an example, when Transformer first came out, it only contains 0.05 billions of parameters. But along with the time, when GPT-2 came out, it already contains 1.5 billions of parameters. And later on, when GPT-4 came out, it already contains more than 1 trillion of model parameters. So that's a huge amount of model size. And this makes us wonder what will happen in the next. And also there is the second trend, which is the diverse on-device deployment requirements, so that we hope to move the deployment of these deep neural network models from central servers to our daily used edge devices. The rationale behind this is that this can help us provide enhanced privacy and data security. So users can do this processing locally on their edge devices and don't need to upload this data to the servers, so they can have better data security. And also this can allow these apps to have offline functionality. So imagine if we are in a scenario and we don't have the access to the internet, but we may still hope this task to be finished. And if we deploy these deep neural network models on our edge devices, this can make it perform well. But like this type of deployment also faces some challenges. The first is the constrained hardware. So comparing to the central servers with huge amount of computation and memory resources, our edge devices usually only have limited hardware resources. And also, our edge devices, they are typical limited battery. We need to charge them to get like enough battery to power these AI applications. And also, for the same DNN application, we are expecting it to be able to be deployed across diverse devices and across diverse environments. And along with this trend, we see there is the recent demands for building sustainable AI systems. So why is that? First is from the environmental level. We know that with the broad applications of these AI models and also the ever-increasing model size, these models are consuming huge amount of energy. And here I show some carbon dioxide emission benchmarks in pounds of carbon dioxide emissions. Take the air travel from New York to San Francisco as an example. It will cost around 2,000 pounds of carbon dioxide emissions. However, if we want to train a latest transformer model with neural architecture search approach, it will cost around 600,000 pounds of carbon dioxide emissions. That's like 300 times for the air travel between San Francisco to New York. So that's like quite expensive. And also, besides the training of the DNN models that only needs to be conducted once, we need to like conduct the inference multiple times. And for the inference of deep neural network models, we take this widely used ChatGPT model as an example. The queries per year will cost around like more than X millions pounds of carbon dioxide emissions. So this motivates us to make these AI systems like more energy efficient so that it will not bring too much harm to our ecosystems. And on the other side, from the social level, because also of these wide applications of these deep neural network models is used, for example, in the disease diagnosis. So in 2023, there are already like more than half of the usage of this AI-assisted diagnosis for us to detect this disease. And also in autonomous driving is quite like safety critical. For all of these systems, we don't hope is to provide like bad results. We hope these systems to generate reliable outcomes. In this case, we can avoid the bad effects or the panics or the loss of trust of these AI systems. And build on these motivations, my research is to achieve the practical implementation of sustainable AI systems from both the environmental level and social level. And today I will cover in each direction of my research. So from the environmental level, I'm trying to make this deployment of deep neural network models more energy efficiently. And I'm mainly using two types of approaches. One approach is named as bottom-up. So for bottom-up, this means given these AI algorithms already determined, how can we design from the system level to manipulate the system level configurations based on the characteristics of the AI workloads to help them run in an energy efficient manner? And on the contrary, which is the top-down approach, this means that given these AI algorithms already determined, how can we design from the AI algorithm itself to make them like more energy efficiently? Also, from the social level, I'm working for the trustworthiness and security and fairness of these AI models. So first, let's look at the bottom-up approach. So I will show an example in this direction. How can I achieve using bottom-up approach to build these sustainable AI systems to make them run more energy efficiently? Before diving into the research details, let me first provide some preliminaries. So on the left-hand side, it shows a mobile platform, which is the OnePlus T8 platform. It's the latest like a mobile platform. And on the mobile platforms, in the table 1, we show the frequency and voltage levels of the GPUs that equipped it on this mobile platform. So typically, our mobile devices, the GPU and its CPU have multiple different voltage and frequency levels. And a higher frequency level is achieved by powering with a higher voltage level. And if we have a lower frequency, usually it will lead to lower power consumption because on the bottom, we show this dynamic power consumption is relevant to both the frequency and voltage squared. So of course, if we use a lower frequency level, usually we can make the devices consume like fewer power. And typically, when our device is in a low battery mode, we will try to reduce the frequency and voltage levels to help it running to save its power so that to achieve a longer availability. So even for the same deep neural network model, it may have quite different latency behaviors under these dynamic voltage frequency scaling scenarios. And in short, it's DVFS. As we all know, DNNs, they have many different interesting applications that can improve user experience on the mobile devices. As mentioned in the backgrounds, it can be used for object detection, photo enhancement, or translations. And also deploy these applications on the mobile devices is quite challenging due to the limited computation resources and also due to the limited battery. So for the same DNN applications, so for the DNN applications to be deployed on edge devices, they may have like different requirements. So some DNN models, they hope to achieve like real-time inference performance. Then in this case, we are trying to address the question, can we reduce the power consumption? And in the same time, we hope to keep the inference speed to be fast to catch up with the real-time inference requirements. And as for some other DNN applications, they may prefer to achieve ultra-low power consumptions. Then in this case, we are trying to see whether we can pursue this ultra-low power consumption, and in the same time, we don't want to influence this speed too much. And in order to provide the system-level configurations for the DNN inference, we are first trying to analyze the characteristics for the DNN inference. So for the DNN inference process, is mainly composed of 3 stages, which is the data pre-processing stage, feed-forward calculation stage, and the data post-processing stage. So for both the data pre and post processing stages, which is marked as the process A and D in this figure, they are mainly actually executed on the CPU. And if we want to optimize the configurations for the data pre and post processing phases, we can consider to manipulate the dynamic voltage and frequency levels on the CPU. And also for our mobile devices, it has the big little heterogeneous architecture. So we can change the type of CPU cores that we are used for these inference stages. And also we can change the number of CPU cores to support the running of these AI workloads. And moving forward, we have this feed-forward calculation stage, which is marked as B and C in this figure. And for the feed-forward calculation, actually, they are mainly executed on the GPU. And therefore, if we want to optimize for the feed-forward calculation stage based on the system-level resources, we can try to change the dynamic voltage frequency scaling on the GPU by adjusting its voltage and frequency levels. Based on these characteristics of the AI workloads, we propose our mock framework to allocate appropriate resources based on the characteristics of different DNN models. And our framework is mainly composed of two parts. The first part is a DNN classifier. And this DNN classifier tries to categorize existing DNN models into 5 different categories, which includes computation intensive, memory intensive, both efficient, CPU intensive, and CPU efficient. So based on the DNN classifier's output, we send it as the information. We send the information of both the model and the system level informations of like what resources we are equipped with the current device into a deep reinforcement learning agent. So this agent will help us to make the decisions across the different running stages for different DNN models. Then let's look into detail. First is the key component of the DNN classifier. For the DNN classifier, we built 2 resource-demanding models. So one is the feed-forward model, and the other is called the CPU memory model. And on the right-hand side shows the example of our feed-forward model. So we can have a look of this example. So in this figure, we can see there are many different colors of the curve. So for each color of the curve is corresponding to a different frequency level. For the ResNet 50 model, we can see that when we change the running frequencies, we can get different attainable G-flops. So this means that the computations of this ResNet 50 model is actually the performance is bounded by the computation. On the contrary is the model which is called WDSR, is used for the super resolution task. For the WDSR model, we can see that no matter how we change the frequency levels, the attainable G-flops does not change. So this means that even though we try to increase this computation capability for running this model, it does not like influence these attainable G-flops. Therefore, this model, the performance is actually bounded by the memory access. And in the middle is the efficient net B0 design. So for efficient net B0, it's still for image classification, but it has a better architecture design to achieve better efficiency. So the efficient net B0, it can either be bounded by the computation or bounded by the memory access, depending on the frequency levels. So here shows the examples of our DNN classifier. And based on the classifier, now we have the DNN categories. And this category information is sent to our deep reinforcement learning agent to help us derive better configurations to support the running of these DNN models. So for the deep reinforcement learning agent, we are using the so-called deep Q learning algorithm. So we are having a deep Q network. It's a multi-head, multi-layer perceptron. It's very lightweight with only 3 fully connected layers and is equipped with batch normalizations and ReLU activations. And during we trying to find these optimal configurations, we are considering from both the power consumption side and the latency side, because we want to achieve like a low power consumption, and in the same time, we don't want the inference speed to be too slow, because in some cases, if we want to achieve like ultra low power consumption, it will use the lowest frequency level, which causes the DNN model to take forever to finish the running. And this speed and power, they are combined together to formulate our reward function. And they are combined together with the so-called hyperparameter alpha to adjust the relative importance among the speed constraint and the power consumption. And for the deep reinforcement learning design, there are 3 key aspects, which is the state space, action space, and the reward function. As we already discussed the reward function, as we will consider both the inference speed and power consumption. As for the state space, we will take into consideration for both the characteristics of our deep neural network models, as well as the device parameters into account. And as for the action space, this is relevant to what system level configurations we can change so that we can achieve our objective of power efficient inference. So here the action space includes like which CPU core cluster we should use, and also which frequency we should use for the CPU cores, as well as the GPU frequency. And also to facilitate better convergence performance of the deep reinforcement learning agent, we propose like 3 rules to help this. The first rule is that in the feed-forward calculation stage, mock will only select actions with little CPU core cluster. The rationale behind it is for the feed-forward calculation, as mentioned in the preliminaries, is mainly like running with the GPUs. So in this case, we don't need to use like a super powerful CPU cores. Therefore, it will only select actions with this little CPU core cluster. And also like in the pre and post processing stages, it will only select actions with the lowest GPU frequency. The rationale is similar. So for the feed-forward calculation, as it mainly relied on the GPU capability, we don't need like for this stage, they are mainly rely on the CPU capacity. So we don't need the GPU frequency to be very high. And also in the pre and post processing stages, we will not choose the CPU core cluster with only 1 core. So this third rule is also like similar to the rationale to the second rule. So for these like 2 stages, as rely highly on the CPUs, we should not like use the CPUs with lower performance. And finally comes to our evaluations of the mock design. So comparing to the coarse-grained configurations in average, we can greatly reduce the power consumption. For example, for the ResNet 50 design, which is a computation-intensive model, we can reduce the power consumption by 6.3%. And for the WDSR, which is a very like memory-bounded model, we can reduce the power consumption by 9.5%. So here, like the power consumption reduction is actually measured by the power meters, which is actually reflecting it's like power reductions. And we didn't like touch any design from the AI algorithm perspective. Only by changing these system level configurations, we can already achieve like more than 5% of power consumption reductions across different type of DNN models. And next, we will move to another direction of my research, which is the top-down approach. On the contrary of like changing the system level configurations to support the running of AI workloads, in the top-down approach, we are focusing in the AI algorithm designs, trying to make this AI algorithm running under different hardware running environments. And here I will show one example of my work. Also, before like diving into the research details, let me first provide some preliminaries. So pruning is an efficient manner to reduce the redundancies in deep neural network models. It will try to prune out some weights and computations from the model so that we can run this model faster and with fewer like computation requirements. And there are 2 fine-grained structured weight pruning schemes in the literature. One is called pattern-based pruning, and the other is called block-based pruning. These 2 types of pruning regularities, they have the advantages of both achieving high accuracy and also they maintain the structures that can make these weight reductions into actual accelerations on the devices by using efficient compiler optimization techniques. So after we prune this model, we can have graph level optimizations, and after that we will have some layer-wise representations, and through computation reordering and load redundancy eliminations, we can obtain the codes to be deployed for the running, and these compiler optimizations can lead to the reductions into actual speed up. So here, let us first consider the question, why the conventional training or the pooling is not in a sustainable manner. So imagine we have a pool of devices with different devices, and if we want to find a appropriate DNA model to be deployed, we have to conduct this individual training based on the device information and the speed requirement. And after the training process, when we come to the deployment phase, typically one set of training will lead to a sparse model, which only works at a fixed sparsity ratio level. And as mentioned in the previous preliminaries, our mobile devices, they have multiple different voltage frequency levels. And when our device is with full power, we will use a very high running frequency. In this case, we can have a very fast inference speed. However, when our device is almost run out of power, it will try to switch to lower running frequencies. And in this case, this will cause the models to have like longer latency, and this is undesirable. So we can see that for the conventional pooling or conventional training, this method is not scalable across diverse device and environment. We have to conduct this individual training based on its requirements. And also this will cause high training cost, because whenever there is a new device or a new requirement comes, we have to train this model again to help us derive an appropriate model. And also it will cause the waste of hardware resources, because when we allocate resources on our devices, we will allocate resources typically based on the worst case running situations. So this means that it will allocate resources based on the longest latency case. And in this case, when our device is actually running with a high frequency, we are actually waste these precious hardware resources. And also, we will face the low consistency issue. So even for the same deep neural network model on the same device, the latency can vary a lot across different frequency levels. And the motivation for my work is that what if we can have an adaptive deep neural network model, so that we only need to train this model once, and we hope this model to work for diverse devices and environments. And also, when we get this model, we hope it can be easily switched on our devices. And in the same time, we hope this model to have stable inference speed on our devices. No matter how the frequency changes, the latency should be a constant. And this in this case, we can greatly save the energy for both the training and inference. And we ask the question whether it's possible for us to have this adaptive deep neural network models. And luckily, the answer is yes. And we propose the condensed framework to derive these adaptive deep neural network models. So again, we have this device pool with different type of devices. And in this case, we will conduct the adaptive model training. So we have the initial model for the application, and we will conduct this adaptive model training. During the training process, we will update the importance values and also the model weights. And after the training process, we can get a sparse-based model and a set of importance values. By combining this sparse model and the importance values, we can transform this model to many different subnets. And all of the subnets, they will share the same set of model weights, and they can work at arbitrary sparsity ratio levels. Therefore, when it comes to the deployment phase, we actually can separate the adaptive model training from its actual deployment. Based on the device information and speed requirement, we can have the reconfigurable deployment of these adaptive deep neural network models. So when our device is with high frequency, when our battery is full, we can use like more computations by using a more dense version of the model so that we can reach slightly higher accuracy performance. However, when our device is the battery is becoming lower and lower and the running frequencies are switching to lower cases, we will remove like more parameters and computations from these deep neural network models. Therefore, we can maintain a very stable inference speed when it's actually deployed on our edge devices. Basically, for a higher frequency level, we will apply it with a more dense version of this deep neural network model. However, when our device is almost run out of power, when it's running with the lower frequency levels, we will switch to a more sparse version of this model. And the good thing is that all of the subnets, they will share the same set of model parameters. So we don't need to store multiple sets of these model weights on our devices. Only one set of model weights is enough. And the condensed training algorithm is based on one proposition, is that the error of the subset is bounded by the second level sparsity error and the first level sparsity error. So during its training, we will conduct iterative updates to minimize the second level sparsity error as well as the first level sparsity error. And in each training iteration, we will sample a set of sparsity ratios from a range and conduct the training and accumulate the gradients to help us update both the model weights and the importance values. And when it comes to the actual deployment on the devices, imagine there is a new device and it has K frequency levels and has the latency requirement T. So we can conduct a very fast binary search process to direct the appropriate sparsity ratio levels to be employed. So basically is that we will have some on-device latency measurement. If the latency is like longer than the required latency, we will adopt like a more sparse version of the model. However, on the contrary, if like the speed is much faster than the requirement, maybe we can switch to a more dense version of the model. And also for the importance values, actually they don't need to be stored in full precision on our mobile devices. We can rescale them into the logic format. It only needs to like change among these K frequency levels. So this can also help us save the memory consumption for the deployment of these adaptive deep neural network models. As for the storage cost of our adaptive deep neural network model design, it's mainly composed of three parts. The first is the sparse-based model. As it's already a sparse version, so it's like contains like fewer parameters and memory requirements comparing to the dense version of this model. And also, we only need to store this rescaled importance values and the threshold values to help us switch among different masks. And the rescaled importance values and threshold values, they are very lightweight comparing to the model weights. So their like storage cost can be negligible. So basically, we are also like saving this storage cost of these sparse models comparing to the storing a dense model on our mobile devices. And also here shows the experiments results. So we examine our performance across different model architectures and different model and also different data sets. On the left-hand side, we show the figures. The x-axis represents the sparsity ratios, and the y-axis shows the accuracy performance. As can be seen from this figure, we can achieve like much higher accuracy performance comparing to the existing works that makes these models works at a range of sparsity ratio levels. And also, we show the latency behaviors when we deploy these reconfigurable DNN models on our mobile devices. So we can see that the reduction rate of the latency variations can be more than like 400 times comparing to using a single sparsity ratio level on our devices, and in the same time, we can achieve like minimal accuracy loss. And besides from the environmental level research to conduct sustainable AI, I also have the research in the social level to make these models work in a trustworthy manner. So here I will show my work, so-called reverse engineering of imperceptible adversarial image perturbations. And also, I will first give some preliminaries. So we have the AI systems which is deployed across different scenarios, and there exist many attacks to fool the decision of these AI systems. For example, there are some adversarial examples or attacks. They are achieved by adding some adversarial perturbations to the original clean image, and this will alter the final decisions of our AI systems. And also, there are some attacks in the physical world by adding some stickers to the stop sign. It will be predicted as the speed limit sign. So imagine these cases happens in autonomous driving. This will cause very severe dangerous. And also there are some adversarial t-shirt. So for people wearing this type of t-shirt, they will no longer be recognized as human beings. And in the literature, there are some defense mechanisms during the inference phases of the deep neural network models, which is so-called adversarial detection. So given an input image for adversarial detection, is trying to figure out whether this is a clean example or is an adversarial example. But my method actually goes beyond this adversarial detection, which is achieved the reverse engineering of deceptions, which in short is RAD. For RAD, we are still get this input image, and we have a reverse engineer. The reverse engineer will try to extract these perturbations from this adversarial input. And based on the extracted perturbations, we can have the analysis of what is the clean label of this original image and what the attack method the attacker is using, and in which area the attacker is trying to attack to achieve this misclassification. And also we can know what is the victim model that the attacker is using to build this attack. And for the victim model, we can have further analysis to know what the architecture the attacker is using, what the activation function is inside this model, and what is the kernel size, as well as our old friends like model sparsity, which achieve the efficiency. And if we have this reverse engineering of deception approaches, we can have a better knowledge of the attacker. So there is a old saying, which is to know yourself and know the enemy, we can to win every battle. So with this reverse engineering approach, we can have a better understanding of the attacker. And in this case, we can achieve better defense against them. And here, our goal is that we hope to reverse engineer, or we hope to recover the adversarial perturbations to make further analysis of the attacker's objective. Then there is one question. So how can we know whether the adversarial perturbation is reverse engineered successfully? Because it's a relative new research topic, we need to have a set of evaluation matrices to help us make these evaluations. So first is from the pixel level. So after the reverse engineering, we extract the perturbation estimates from the adversarial image. We should have a clean image estimate. Therefore, in the pixel level, actually, we hope the recovered clean example to be as close as the original clean example. And also for the prediction level, because these attacks will make these AI systems to have like misclassifications. And after, for the prediction level, we hope the recovered clean example to have the same prediction as the original clean example, so that we know that we are actually recovered these perturbations from this adversarial image. as well as the reconstructed adversarial image, it should have the same prediction as the adversarial image itself. So this is from the prediction level. We also can evaluate the performance of the red performance. And the third level is called attribution level. So for the attribution level, what we are doing is that we hope to attribute the predictions of the classes back into the input saliency region by GradCam. So in GradCam, we can have the input attribution, and we hope that there should be the alignment between the recovered clean image with the original clean image. And also for the reverse engineered adversarial image, it should closely align with the original adversarial image in the attribution level. And here is a master try baseline, which is called denoising only, because we are trying to extract the perturbations from adversarial image. Is similar to the denoising problem, which we want to denoise the noise from the input image. We can view these perturbations as a kind of noise. In this case, we can train a denoiser to minimize the difference between the denoised examples and the clean examples. And from the experiments, we found that denoising only baselines, they can actually achieve good performance in the pixel level. So the recovered clean image is very close to the original clean image. But we found that they are far away for the prediction alignment. So for the recovered clean image, it usually does not have very close predictions as the original image. And also is far away for the attribution level too. So here shows an example in the attribution level. We are using GradCam. So for GradCam, what it works is that it's trying to see what does the deep neural network see to make these the classification decisions. And it's trying to localize the input patterns used for a certain prediction. So as we can see from these figures, the left-hand side shows the input image. In the middle is the performance of the denoising only approach, and the right-hand side is the ground truth. We can see the saliency regions between the baseline and the ground truth is quite far away from each other. So this is not desirable. And based on the limitations of the denoising only baseline, we propose our class discriminative denoiser with data augmentation approach. So basically, it's trying to incorporate two techniques. The first is the prediction alignment, and the second is the data augmentation. So for the prediction alignment, we are trying to boost the prediction level alignment that the denoising only approach fails. And also, we are using the data augmentation approach to boost its denoising ability by using multiple views of the same data. So here for the data augmentation methods, we are considering rotations, flipping, and translations. First is the components of the proper data augmentation. Imagine why the data augmentation can boost our denoiser performance is that an adversarial instance, actually, they can be sensitive to input transformations. So this means, for example, the original adversarial image, they may fool the classifications of our AI systems. However, if we flip this image, maybe this perturbation does not work anymore, and these AI systems may be able to have correct predictions. So this can allow RAD to focus on the most informative attack artifacts. And also, these benign and adversarial instances, which are resilient to transformations, they may be enhance the prediction and input attribution alignment. And here shows a study of using different data augmentation methods and to verify its performance. Basically, the x-axis shows the performance in the pixel level, and the y-axis shows the performance in the prediction level. And a good performance should be in the the top left part, which shows like better performance than our baseline. And in these cases, we found out by using cut mix and crop pad, it can help us enhance the read ability. And in our experiments, we combine these two types of data augmentation methods. And finally, we have our read evaluations. So we can see that for our approach, we can maintain like a relative good, like a pixel level performance, and in the same time we can greatly boost in the prediction levels and also in the attribution alignment level. Here shows the example that I shown like in previous examples, and our method is marked with these red boxes. As you can see from this figure, our like attribution alignment is greatly matches with the ground truth. And also, we show the intersection over units across the entire test data set to see the attribution alignment. So a higher intersection over units, or like a higher IOU, means a better performance. And again, our methods have a higher concentrations in the higher value regions, which means that we have better performance also in the attribution level. And also, RED is able to recover the adversarial perturbations even on some unforeseen attack types. And this RED performance can actually be extended to many application scenarios. The first application is trying to infer the adversarial's identity. So imagine we have a new attack that we never seen before, and we can recover the perturbation with our RED approach. And based on the extracted or the recovered perturbation, we can conduct correlation screening based on the known attack library. So we can see like how the new attack correlated to the known attacks in the known attack library. So which attack is more like similar to. So in these cases, we can try to figure out from the known attacks, which this new attack is the most similar to. So this can help us defend against some like new attack types. And also, it has the applications to uncover the victim models for transfer attacks. So for transfer attacks, this means that the attack is generated on a model A, but this attack can also to fool the classifications of model B. Then in this case, we want to know the true source of the model that the attacker is using to craft these adversarial perturbations. And this can also achieved by our RED approach, and we can view it as a model parsing problem. It can help us review the true victim model that the attacker is using. Instead of it will make the predictions to the model B, it will predict that the attacker is truly using model A to craft these adversarial perturbations. And when we uncover the victim model attributes, we consider to uncover its specification performance, whether it's a dense model, it's an unstructured prone model, a structured prone model. And also, like, we want to uncover the activation functions it's using, whether it's using tangent H, ReLU, or eLU functions. And also, what is the kernel size of this victim model, as well as what is the architecture of this victim model. So here shows the applications to uncover the victim model attributes. So again, we have the adversarial image input. We put into the RED denoiser network so we can extract the adversarial perturbations. And these perturbations is used in a model parsing network based on supervised training to tell us the model attributes of this current model. So in the bottom left side shows the transfer attack success rate. So basically it shows like the x-axis shows the transfer attack model, and the y-axis shows like the original victim model to craft this adversarial attack. So from the figure, we can observe that First is the lighter means that the transfer attack success rate is higher. Basically, the diagonal one means the victim model and the attacked model, they are the same, so they have the highest like attack successful rate. And the Railu functions models seems to have like to be hard to be transferred among all of the different models. One possible rationale is that the Railu function is the only like non-continuous activation function type comparing to tangent H and Yilu, so makes this like transferability to be harder. So maybe when we like have some defense mechanisms when the attacker is crafting the adversarial perturbations using a victim model with Railu activation functions, we can switch our current model's activation function types to make these models being like not successfully attacked. And also we can see that the attacks crafted for a certain sparsity ratio level is easier to transfer to a model with a different sparsity ratio level. And our approach can reveal this true identity of these victim models, which is shown in the right-hand side. And based on my past research, here moving forward, I hope to talk a little bit about the new challenges brought by the large-scale models for the generative AI. So in the shorter term, I have some like research plans as nowadays the models are moving from the discriminative task to generative task. So I have some like short-term plans, including the efficient and trustworthy foundation model building, as well as generative AI-powered chip design. So for the first plan, from the algorithm level, we can study the efficiency of inference scaling laws. And also it's important for us to build vision foundation models. And from the system level, we need to study mixed precision training and inference, how to like achieve the hardware level implementations. And also, we can conduct reverse engineer of the attacks for these generative models, as well as machine unlearning for these large language models to remove some sensitive data. And for the other direction, will we have these powerful generative AI models? The other direction is that we can have energy efficient chip layout design. Maybe we can search for optimal chip configurations with low power consumptions with the help of generative AI techniques to help us from the hardware level also reduce the power consumptions of our AI systems. As for the longer research goal is that we know that human intelligence actually consumes much less energy comparing to large language models. And I'm trying to see whether do we really need this huge amount of energy and cost for training foundation models. And I hope to pursue the ultimate efficiency to democratize the powerful AI systems to everyone. So instead of currently only the large companies, they have these computation resources and have the money to build foundation models. I'm hoping to have like ultra low cost of these foundation models. Maybe this cost can be under thousands of dollars so that every researcher can have the ability to contribute for the build of these foundation models. In these cases, this can foster the collaborations in the research and also have like more research outcomes. And also we know that with great power comes great responsibility. When we have these AI models with like cheaper price and be deployed across everywhere, we hope it to work in a secure, trustworthy, and fair way so that it can be used to facilitate faster science breakthroughs and bring more convenience to our daily life. Thank you, everyone. Yeah, that's all my research.
Any question from the audience?
Good question. How does DeepSeek fit into this? Have you looked at that?
Yes, so that's a great question. So here, this DeepSeek design actually is kind of a motivation also to my longer research goals. So previously, actually, we are believing for these large-scale models, we need to scale the model size and train it with like more money. But when like DeepSeek came out, it only used like 5 million training cost to have like a comparative performance as GPT-4, which costs like more than hundreds of millions of dollars. But still, like it's not enough. It's still quite expensive. It's hard for academia to pursue this foundation model pre-training with such large amount of like a cost. Therefore, like my automated like research goals is to further reduce the reduce the consumptions of the training of these foundation models by pursuing the ultimate efficiency of these generative foundation models. As for DeepSeek, like it has some like efficient designs. For example, it's using distillations to transfer the knowledge from the powerful models to it, and also it's only use like a mixture of expert designs that activates parts of the model to conduct the inference so that it can reduce the cost for every query. So all of the techniques we can learn from it and to help us build these sustainable AI systems with like less power consumptions.
Yeah, since it's open source, can you actually use it in your research?
Yes. For example, for the DeepSeek design, we can leverage its power. For example, we can leverage it for the Gen AI powered chip layout design. For example, because it's open sourced. So for the specific task for the chip layout design, we may be able to fine-tune this DeepSeek model on a small subset and also across a small amount of parameters to make it tailored for the specific task to have good performance. And this type of research can also like bring like more efficiencies if we have like more power efficient chip layout designs. Hope I'm like answering your questions. Yeah, thank you. Yeah, please.
When you do the adaptive pruning, have you measured overhead? Like, are you going to load the model again and remove weights, or how are you going to do that?
Yeah, so that's a great question regarding the overhead of the adaptive neural models. So imagine the good points of our adaptive deep neural network model design is that all of the models, they are sharing the same set of model weights. We only need to apply a certain mask to it. And the switching of these models can have like very low overhead. And whenever like the frequency switches, we can use this like switch the model for inference for multiple times. So the switching is not like a huge amount of cost comparing to the inference itself, like due to our design that the subnets they share the same set of model weights.
The model stays in memory and just applying this mask.
Yes,
it's
so
not much overhead for the mask.
Yes, so it will like mask out some like redundant weights that we don't hope to use for a certain sparsity ratio level based on the current running environments. Thank you. Yes, please.
Yes, thanks for sharing. I have a question regarding to the bottom-up method. So now the chips, most of the chips already like incorporate with the neural processing unit. Then do you think that this NPU will change your workflow, or they already solve the power efficiency problem?
Yeah, so that's also like a very great point. So with the involvement of the hardware designs, we can also still have this like bottom-up approach by leveraging the characteristics of these deep neural network models. We just need to take this newer level of like system level configurations into consideration and train this deep reinforcement learning agent to derive these new solutions with these new like hardware designs. Yeah, so it's still like the method is still applicable, but we need to like retrain the models based on the new hardware environments. Thank you.
Okay, so time is up. Thanks to the speaker again. So if you have any questions, just Please come and then chat with her. Thanks for attending.